Hello everyone. So welcome to the second lecture for the 13th chapter nuclear of the unit atoms and nuclei. So till now we saw how we get atomic mass number, how we get the size of the nucleus, okay, and we also saw that with constant development and more investigations, people understood the presence of neutrons, which actually gives the different atomic mass numbers to all the elements. And because of the presence of neutrons, we understand that there is a the existence of isotopes of different elements. We have isotopes, we have isobars, we have isotones. Okay, all of them have a different relation or different ratio of number of neutrons or number of protons. Okay, so this is what we have done till now, and even the last thing that we saw was nuclear force. How it was one of the most it is stronger than your Coulomb force, your electrostatic force of attraction or repulsion, as well as it's stronger than even the gravitational force. Okay, so we had seen all this, and now we will move on to very important part that is, associated with nucleus of an atom, that is the radioactivity. Okay, so Becquerel was the scientist who discovered radioactivity. It was by accident. Okay, so he was actually understanding the phenomena of fluorescence and phosphorence of compounds. So when he was doing that, he actually wrapped some uranium and potassium sulfate pieces of those samples, and he put them in black paper, and he kept it on a photographic plate. Later on, when he developed this photographic plate, okay, so he saw that there was some amount of blackening that was there, and that he assumed or he found out was due to some kind of energy or something that was emitted by the compound. Okay, and it was able to penetrate through the black paper that was wrapped, and also the silver the silver plate that was separating the sample from the photographic plate. So he conducted not he, like later on there were experiments conducted, and that's when people started understanding the entire radioactivity of of a nucleus, the phenomena of it. And what it essentially is that the unstable nucleus, okay, we have seen that neutrons within the nucleus is stable, but if suppose a neutron is kind of ejected out of the nucleus, it will get unstable, and then you will have something that is called the radioactive decay. Okay, so in the radioactive decay, you will have, just wait a minute. Yeah, so in the radioactive decay, you have three types of decay. Okay, three types of decay. Okay, so you have alpha decay actually. Okay, where your helium nucleus is emitted. Okay, we will see this in detail. Okay, so a helium nucleus is emitted. Okay, and then you have your beta decay. Okay, so in beta decay, you will have either electrons, so that is negative beta particle or a positive beta particle. Okay, so they are electrons or positrons. Okay, so they will be emitted. Okay, and then you have gamma decay. Okay, so in gamma decay, you have, high energy photons are emitted. Okay, so these are the three types of decay. So we will learn about each of the decay. Before that, we will first try to understand what is the law of radioactive decay. Okay, so there is a certain principle that is followed by these, these particles which are emitted. Okay, particles or energy that is emitted due to the three radioactive decay patterns. Okay, so in any radioactive samples, when it undergoes alpha, beta, or gamma decay, okay, what experimentalists have found is that the number of nuclei that is actually undergoing the decay per unit time is proportional to the total number of nuclei that was there in the sample. Okay, that is there in the sample. So if you have, say, n is the number of nuclei in sample, okay, and your del n undergoes decay, undergo decay in del t time. Okay, so this will be actually given as del n by del t, okay, and it is actually going to be proportional. Okay, so the amount of the nuclear that is decaying in the time interval del t is going to be proportional to the initial is the total number of nuclei that is there in the sample. Okay, so now to remove the proportionality, we have to introduce a proportionality constant, so that is actually lambda. Okay, so lambda n. Okay, so this is what we get, where your lambda is called the radioactivity decay constant. Okay, or it is also called the disintegration constant. Disintegration as in your nuclei is actually disintegrating into different nuclei constant. Okay, so this is the law. This is the law that the number of nuclei that is undergoing decay per unit time, okay, is proportional to the total number of nuclei that is present in the sample. So this del n by del t, okay, there is then supposedly there's a rate of decay that exists. Okay, so there is going to be a rate of decay. That rate of decay or rate of change of n is actually given by dn by dt is equals to minus lambda n. Okay, so this is the rate of change of n. Rate of change of n. Okay, or we can then write it as dn by n equals to minus lambda dt. Okay, now if we integrating both sides, we will get integrating from n0 to n, and dn by n is equals to minus lambda comes out since it's a constant. So from t0 to t dt. Okay, if you expand and then you get is that ln n, this is natural log of n minus natural log of n0, okay, is equals to minus lambda. This would be t minus t0. Okay, now what is this n0? N0 is the number of radioactive nuclei at some time t0. Okay, and then n is the number of number of radioactive nuclei at any time t after t0. Okay, if you consider t is equals to t0 is equals to 0, okay, then you can find the the proper equation where you will get the exponential decay that the radioactive nuclei undergo, so that you can get if your t0 is set to 0, then what you are left with is ln n by n0 is equals to minus lambda t, which can be finally written as n t is equals to n0 lambda t. So this is actually the equation that we usually use to understand the radioactive decay. Okay, so the decay of the radioactive, the decay of radionuclides is, kind of following this law, most of them. Okay, but there is another term that is associated, that is called the total decay rate, R. Okay, so how we give R as R is equals to minus dn by n. Okay, so it is actually the number of nuclei that is disintegrating per unit time. Okay, and over here we will write R as equals to this is the decay rate, the total decay rate. Okay, now again, if you differentiate this, what you're left with is R lambda. We have already seen dn by n is equals to minus lambda dt. Okay, so if you put everything that was there and you differentiate, you get this. Okay, or R is equals to R0 T minus lambda T. Okay, now this you can see this is again equivalent. Okay, equivalent to the kind of equation that we got here. Okay, so equivalent to nt is equals to n0 e raised to minus lambda t. Okay, so then again, okay, if t0, sorry, if t equals to 0, okay, then we can write this as R0 is equals to lambda n0. Okay, therefore R at any time t, okay, can be given as the disintegration constant multiplied by the total number of nuclei that are present. Okay, not nuclei, sorry, nuclei. Okay, so this is what we get. So the decay rate is actually, just the decay rate is at any time. Okay, this is actually, I can write it here again, lambda n. Okay, so this decay rate is actually a much more easily measurable, quantity, and it is usually understood by the terms activity. Okay, so activity. And the SI unit for this activity is becquerel, which is given after the scientist who actually discovered radioactivity. And then there is another, unit that we use, that is Curie. Okay, so Curie, actually this is again named after a very famous scientist, Marie Curie. Okay, a female physicist as well as a chemist. Okay, and she had also won the Nobel Prize for this. So one Curie, okay, is actually equal to one CI. Okay, CI is the you know, denotion or the notation that we use. Then 3.7 into 10 raised to 10 decays per second. Okay, and that is actually equal to 3.7 into 10 raised to 10. Your BQ, that is becquerel. Okay, BQ is becquerel, CI is Curie. Okay, so this is what we understand as these are the units that we use to understand radioactive decay. Now, the radionuclides that are actually decaying, okay, they differ in the rate. Okay, so the rate of decay of different radionuclides is different. So to understand this, the rate of decay and also the age of these radionuclides, there is a term that we use that is called the half-life. Okay, so half-life is actually given by T half. Okay, it is a time that is taken by the sample to reduce to half of its initial number. So if your initial number is initial number is n0, so T half is the time that the radionuclide takes to decay to n0 by 2. Okay, so this is what we understand. This is actually n0 by 2. Okay, so how do we denote this? We denote this by using the radioactive decay, the law of radioactive decay. Okay, this is the kind of this is the equation that we are going to use. So in this equation, okay, so first I'll just write it n equals to n0, okay, n is equals to n0 e raised to minus lambda t. Okay, so this is the equation that we are going to use. And now to understand the half-life, we are going to consider the following. N will be equal to n0 to, okay, so this is the n at any time t. Okay, so suppose we are considering at any time, at time t half. Okay, at time is equal to t half, your n becomes n0 by 2. Okay, the entire n0 by 2. Okay, and then what we get is T half is equals to ln2 by lambda. So that is actually 4.693 by lambda. Okay, so if n0 is reducing to half of its value in T half, similarly, what we had seen, the rate of change, the rate of decay R also will, follow the similar kind of, pattern. R0 will also become R will also become then R0 by 2 actually. Okay. R say at any time t. Okay. So this is how we find the t half. Okay. So this lambda actually varies from element to element. Okay. Varies element wise. Okay. So as for the element that is being used, your lambda varies and then your t half will vary. Okay. Another measure of the know how the radioactive decay is taking place is the average or mean life tau. Okay, so you have another yeah, I'll just write it. I missed mentioning this point. Average or mean life. Okay, so that is tau. Okay, so the number of nuclei that is going to decay in the time interval from t to say t plus del t. Okay, so del t is the interval. Okay, and then we will have that as rt del t. Okay, and that is going to be equal to lambda n0 minus lambda t del t. Okay, so this is, we are including both the radioactive law of radioactive decay as well as the one which we saw for the rate of decay. Okay, and so each of them would be living only for the time t. Okay, so it is only alive or it has only been present for the time t. Okay, so some nuclei may live for shorter time while there are others which live for longer. Okay, as we said that it varies from element to element. So to understand the mean life, we have to integrate the expression, okay, all over from 0 to infinity. And then we can divide the total number n0 of nuclei at time t0. Okay, so how we will get tau is equals to tau lambda n0 0 to infinity t e minus lambda t dt by n0, okay, is equals to lambda 0 infinity t e minus lambda t dt. Okay, so we are integrating on both the sides and we have taken out the constants. Okay, and if you complete this integration, then what you are left with is tau is equals to 1 by lambda. Okay, so if your tau is equals to 1 by lambda, then what becomes your t half? Your t half is equals to tau ln 2. Okay, because we saw t half is equals to ln2 by lambda. Okay, so it becomes t into ln 2. Okay, so these are the two measures that we use to understand the life of a radionuclide. Okay, how long it is going to take to decay, or how much of it has already decayed. Okay, so radioactive elements like, tritium, plutonium, these are, short-lived, and their half-lives are actually, much less than the age of the universe. You must have also heard about, some dating techniques with uranium, potassium, or, carbon dating. Okay, so all these have unstable nuclei, and because of their unstable nuclei, they will decay. Okay, and in time, if we know their T half, we can say how old that material is which has these radionuclides. Okay, so that is why it's it is important for us to understand the phenomena of radioactivity. Okay, so the types of radioactivity, as we have already discussed, is alpha, beta, gamma. Okay, so first let's look at alpha. So in alpha decay, mostly, if you consider, say, uranium, okay, we'll take uranium as the example. So we are going to consider the isotope 238. Okay, so we are going to consider U238 and 92. This is the radionuclide, and when it undergoes alpha decay, okay, so alpha decay is what it relates is your atomic mass number reduces by 4, okay, and your atomic number is reduced by 2. Okay, so your new atomic mass number will be 4 less than the original nucleide's atomic mass number, and your new atomic number is going to be 2 less than the initial sample. Okay, so what you get then is thorium, which has the atomic mass number as 234 and the uh, atomic number as 90. Okay, and what is the particle that is emitted? That is actually a helium nuclei. Okay, so this is your alpha decay. So in general form, we can write whenever we are trying to deal with the alpha decay is that X, okay, this is your original element, okay, this is A, sorry, okay, and when it decays, your new element will have A minus 4 as the atomic mass number and Z minus 2, okay, and plus 1 helium atom. Okay, so this is what we get. Now this kind of decay is very spontaneous. Okay, and from the Einstein's mass energy equivalence, we can see that such a decay is only possible when the total mass of the decay product is less than the mass of the initial nucleus. So in this sense that the mass of thorium is much less, okay, is less than the mass of the uranium. Okay, so this is what we understand from this, and you can check this also by seeing the periodic table or the table which includes nuclear masses. Okay, then the disintegration energy. Okay, or it is also called the Q value of a nuclear reaction. Okay, it is the difference between the initial mass energy and the total mass energy of the decay products. Okay, so for alpha decay, your Q can be given as mx minus my. Sorry, this will be capital Y. Yeah, so my, okay, minus mHg C square. Okay, so this is how the form E is equals to mc square. Okay, from the Einstein's mass energy relation. Okay, so this is the mass of the parent nucleide, parent radionuclide. This is the daughter nucleide, and this is the helium that is emitted. Okay, so you can get it like that, and Q then is actually the net kinetic energy. Okay, net kinetic energy that is gained in the process. Okay, and if the initial nucleus X was at rest, okay, the kinetic energy is the of the products. Okay, and if your say Q is more than 0, okay, So this is actually the alpha decay is causing exothermic reaction. Okay, it is causing an exothermic reaction, or the process is exothermic in nature. Okay, so the heat is given out when your Q is equal more than 0. Okay, then we go to beta decay. Now in beta decay, the essential thing to understand is that what it emits is an electron or a positron. Okay, so electron is a negative beta particle and positron is a positive beta particle. Okay, so one of the examples is actually P 32, 15. Okay, it goes into S 32, 16. Okay, plus E minus is V. Okay, so this is for your beta negative, and for beta positive decay, the example would be Na22. Okay, so this is actually phosphorus that is, decaying to sulfur, and then you have sodium decaying to neon. Okay, this is a positron. Okay, plus V. Okay, so the decays that are seen, this is actually governing by the either the electron that is getting emitted, or it's a positron. Okay, and usually one cannot predict which way the nucleus is going to decay, but you can, as usual, characterize the decay by half-life. Okay, so if you know the half-life of sodium, so you know that, which is a daughter nucleus that is going to be produced. Okay, so for example, your T half for phosphorus is actually 14.3 days, whereas your T half for your sodium is actually going to be 2.6 years. Okay, so you can see that the emission of, the emission, okay, of beta particles will have, based on the type of element, it can have two different T halves. Okay, and these, plus this kind of, what are these particles? These are actually called, neutrino and antineutrino. Okay, so in beta negative decay, sorry, yeah, in beta negative, you have a positive over here. Okay, so actually the since your electron is getting emitted, so what you get is the antineutrino, and what you get in the positive beta decay is neutrino. Okay, so these are kind of, two different elemental particles that are emitted along with the decay. So in general term, you can see over here that with the electron being emitted, your atomic number is actually increasing by, because if one electron is given out, that means the number of proton is more. Okay, we know that the number of protons and electrons are the same in an atom, but if an electron goes out, okay, then what you're left with is an excess of proton. So so the number of the electrons that go out, that is the number of, the excess protons that you have. Okay, so in the beta negative decay, your Z is going to get increased by 1, okay, from the parent to the daughter. Whereas if you have a if you have a positive beta decay, your Z is going to decrease by 1. Okay, so in general terms, how we can write this as, for beta negative decay, okay, N is P plus, okay, so, and for beta plus decay, okay, over here you can say this is the conversion of neutron to proton. Okay, and this over here will proton is equal to neutron plus V. So this is conversion of proton to neutron. Okay, so what you have is X, A, Z. What it turns into, okay, is actually Y, A, Z plus minus 1. Okay, plus you have electron plus or minus, plus you have V or V. Okay, so plus minus 1. So plus 1, if you have negative beta, that is electron coming out, and it would be minus 1 if you have a positron coming out. Okay, and if you have a negative beta decay, you will have your antineutrino. If you have a positive beta decay, you will have a neutrino. Okay, so this is the understanding of beta decay. Now we have gamma decay. Okay, so gamma decay is essentially actually the energy. Okay, it's the photon which is produced. Okay, so you can see that if suppose you have a nucleus that is at the excited state, so when it decays, okay, to a ground state or to a lower energy state over here, a photon is emitted. Okay, a photon will be emitted. The photon's energy is actually equal to the difference in the two energy levels. Okay, so the energy emitted is the difference of these two levels. Okay, so this is called the gamma decay, and the energy in mega electronic volts is corresponding to the radiation of the extremely short wavelength radiation, that is shorter than your X-ray rays also. So when a gamma ray when a gamma ray is emitted, okay, uh, it is also sometimes accompanied with when you have alpha or beta decay, okay, and it results in a daughter nucleus which itself is in an excited state. Okay, then again this will return to the ground state, okay, where single photon transition or multiple transitions are involved, where you can have more than one photon release. Okay, so one of the examples could be, the de-excitation of nickel nuclei, okay, and which is formed by the beta negative decay of cobalt. We can see over here. Okay, so you have your beta negative decay over here. It comes to the energy level 1.17 MeV. Okay, then again it will have another transition. Okay, and again your energy is again released. Okay, so with gamma decay it will come down to another level. Then with further gamma decay it will come down to the non-excited state, that is the nickel state. Okay, so this is the gamma decay. Now we come to the very important part, that is, where the application of all the things that we have learned till now about the nucleus comes, is the nuclear energy. Okay, so we know that you can produce power with, nuclear reactors, and these nuclear reactors, the principle that is followed by them is actually nuclear fission or fusion. So we will first try to understand the two phenomena, fission and fusion. So how do we know this nuclear and nuclear energy is the, we had talked about binding energy in the previous, part of this chapter. Okay, so binding energy per nucleon. Okay, so you have your EBN. Okay, and this is the graph of EBN versus the mass number. Okay, and we had also said that between say 30 to I think 170, yeah, 170, you have EBN is almost constant, okay, for all the atomic numbers between 30 30 to 170. Okay, so it's almost constant, that you have that long flat middle range. Okay, and for lighter elements, okay, that is A below 30, okay, or with A above 170, the binding energy per nucleon is lesser than the constant value. Okay, so the constant value is actually 8.0 MeV. Okay, so below A is equals to 30 or above 170, okay, so your EBN is actually less than 8 MeV. Okay, so this is what we had seen and this is what we are seeing now. So the greater the binding energy, the less is the total mass of a bound system. Okay, that is a nucleus that we are talking. So if the nuclei has less total binding energy, okay, so to transform it to, nuclei with greater binding energy, we need net energy release. Okay, because we saw that, these are high binding energy. So if we have to convert it into to either, heavier or lighter heavier or lighter nuclei, energy needs to be released. Okay, energy will be released. Energy will be released. So when this happens, okay, so if you have a heavy nucleus, okay, decaying to 2 plus or 2 or more, okay, more than 2 mass fragments, okay. So I'll just add 2 or more, nuclei masses. Okay, nuclei masses. Okay, this is actually fission. Okay, the your heavy nucleus is actually decaying into lighter, nuclei. And if, say, light nuclei, okay, fuse together to form heavier nucleus. Okay, to form heavier nucleus. Okay, so that is your fusion. So any of the elements that have, between between 70 to 170. Okay, so if it is decaying, okay, and that it is coming to the, lower spectrum of the atomic mass number, you will have fission, okay, decaying. And if any of these, between 30 to 170 is actually fusing together to form a, bigger, a heavier nucleus, okay, so that is actually fusion. Okay, so first we will see fission. Okay, so the most important, kind of the most important radioactive or nuclear reaction is actually the fission. We use fission in our nuclear reactors the most. Okay, so the example, the most common example is when your uranium 23592 is actually, bombarded with neutron. Okay, so bombarded with a neutron, it will actually, this will be plus, yeah, it is bombarded with the neutron. Okay, so what it gives out is 236, okay, which in itself is unstable, so, and it is radioactive, so it will start decaying. Okay, so it then decays to Sb antimony and 51, okay, plus neodymium 33, 41, okay, and it again gives out neutrons. Okay, so this is one of the examples, okay, of a nuclear fission reaction. Another one would be if you are bombarding your uranium again, 235, 92, okay, into xenon, 140, 54, okay, plus strontium, it gives out, okay, it decays to 58, plus, and then it gives out 2 neutrons again. Now these neutrons, okay, which are being given out, this can again, continue the nuclear reaction. Okay, it will bombard the the leftover uranium nuclei, okay, and the reaction continues. Okay, so this is how usually the fission reaction works. These are the two examples where you use thorium. So the energy that is released, the Q value, okay, is of the order of 200 MeV per fissioning nucleus. Okay, so how can this be estimated? So suppose we take A is equals to 240, okay, and it is breaking into two fragments of A is equals to 120. So EBN, okay, for A is equals to 240 will be actually equals to 7.6 MeV, okay, whereas EBN for two of nuclei with, atomic mass as 120, okay, the fragments, and that is actually going to be 8.5 MeV. Okay, therefore, so the gained energy, okay, the gained energy, that is the binding energy, okay, binding energy for the nucleons or nucleon is actually 0.9 MeV. Okay, therefore, total gain in EVN, the binding energy, is actually going to be 240 into 0.9, okay, or 216 MeV. Okay, so this is how we, get the energy. You can see this is a very high energy that is, released, okay, when you have your fission reaction going on. And this energy, the source of energy, that is there from the nuclear reactors actually can help in producing electricity. So this is a source of energy, okay, that, sorry, the source of this energy, okay, this high energy is actually the nuclear fission. And this is used to produce electricity. Okay, also you might have seen or you might have heard of atom bombs that are used. Okay, so even in atom bomb, you have a nuclear fission reaction going on. Okay, so you can have nuclear fission reaction that is controlled or that is uncontrolled. So controlled nuclear fission reaction can, help you in producing energy, whereas uncontrolled nuclear fission is actually disastrous, and that is where your atom bomb, you can create atom bombs for that. Okay, so nuclear reactors are important for us because it's one of the, they say it's cleaner source of energy, as in you don't have to burn coal or those fossil fuels are not required for energy being produced in nuclear reactors. Okay, so the principle that is there, that the release of the extra neutrons, okay, we have seen that plus 4 neutrons or 2 neutrons that are being produced. Okay, so there is a release of them in the fission process, and on average you have 2.5 neutrons that are released per fission of uranium nucleus. And these because some events produce 2, some produce 3, some produce 4. Okay, so average you can take as 2.5 neutrons that are being produced by the fission reaction. Okay, so the extra neutrons in turn can initiate further fission processes. Okay, and this is the chain reaction. Okay, so this chain reaction you can try to control it. Okay, you have to control it, because if it becomes uncontrolled, then you are going to have the disastrous results that is associated with the atom bomb. Okay, so the average energy of the neutron that is produced in the fission is 2 MeV, and these neutrons need to be slowed down, okay, so that they do not just start interacting with all the uranium nuclei that is present. Okay, and if there are very low number of uranium nuclei, it will get exhausted very soon, and otherwise we need a very large amount of fissionable uranium material to sustain the chain reaction. Okay, and now that we know that uranium in itself cannot be found in very large amounts. Okay, it is a very, we have shortage of it, we have less amount of it that is present naturally. Okay, so to control this interaction, okay, between the neutron and the uranium nuclei, we need something called moderators. Okay, so they usually we use water, heavy water or graphite as the moderators, okay, along with the uranium nuclei to slow down these fast neutrons. So because of these, because of these moderators, there is a ratio K. Okay. So the what is the ratio K? That is the number of fission, products that are produced by a given generation of neutrons to the number of fission of the preceding generation. Okay. And it could be greater than 1. Okay. But it is also multiplication factor. So actually that is giving you the growth of the, the growth rate of the neutrons in the reactor. So if you have K is equals to 1, okay, the operation of the reactor is said to be critical. And this is what we need. Okay, so this is what we need for steady power operation. If K goes more than 1, it is supercritical. Okay, supercritical, and it is not a good condition. It is dangerous. Okay, it is dangerous. You have seen or you have heard of the Chernobyl disaster. Okay, so this is one of the reasons that happened. It became supercritical and it exploded. Okay, and reaction rate is therefore controlled through control rods, which are made from neutron absorbing material. Okay, so this actually controls the, or it absorbs the excess neutrons that are being produced. Okay, and it is required with the control rods. We need safety rods. Okay, and this can be actually inserted into the reactor where the K again can be reduced to less than unity. Okay, so the kind of the more abundant the if the number of neutrons are actually increasing at a very high rate, you can just put these safety rods into the reactor chamber and it can absorb the neutrons. So the the very abundantly found isotope is actually 238. Okay, so 238 uranium is the most commonly used, and it is the natural occurring. Okay, and it is non-fissionable. So how do you convert it to something that is that decays and then it gives out that energy that we need. So you bombard your U38 with neutron. Okay, and with that you are going to get your 239 uranium, okay, which then starts decaying. Okay, so you have your 239, 93, and this is the beta decay that we have. Okay, this is the beta decay, and then this in itself, okay, this is the plutonium, then then the plutonium itself then undergoes the further radioactive decay. Okay, so plutonium is then formed into 4 plus or minus. Okay, now this actually undergoes fission with slow neutrons. Okay, slow neutrons. Now you can see that this is kind of the schematic of the nuclear reactor. Okay, so this is a thermal neutron fission. Okay, so this is actually where your thermal neutron fission takes place, this reactor. Okay, yeah. So the core of the reactor is the site of the the nuclear material. Okay, that is kept, the nuclear fission material. Okay, this is where we have it, contains the fuel elements in the proper form. Okay, it could be enriched uranium, which has greater abundance of 235 than the naturally occurring 238 uranium. It also has the moderator. Okay, it has the control rods. So it has all of these. Okay, and kind of coolant is supplied. Okay, so because as energy is released due to the fission reaction. Okay, so we need to stop the overheating, and for that we need coolant. Okay, so we need to use a coolant, and this kind of this is put into a containment vessel, okay, which prevents the escape of radioactive fission products. Some radioactive fission products can very easily penetrate through, these containment vessels. So we need a proper containment vessel of that. Okay. And the reactor can be shut down by means of rods. Okay. So, for example, cadmium rods, which can absorb, high amount of neutrons. Okay. If it absorbs all the neutrons, free neutrons that are there, then no more fission reaction can take place. Okay. So the coolant then transfers the heat to a working fluid, okay, which in turn then produces steam, and this steam drives the turbines and then generates electricity. So the coolant actually drives the heat out from the core, and then it's it supplies to the turbines, okay, where your steam is first produced, and then it goes to the turbine, and then the heat is exchanged, and your electricity is generated. And then once the heat is kind of removed and converted into steam, the water that is remaining is again condensed, and then it acts as the coolant. So this is like a cyclic process. Okay, so though, as I said, that this does not use any fossil fuels and it is much, much safer. Okay. So, but there is a lot of nuclear waste that is generated, and it needs to be especially taken care of, and it could be hazardous if it is just left, out, just in, open. So you need a proper waste management for nuclear waste. Okay. Now, quickly, we'll go to the next important reaction of, when nuclear energy is produced is your nuclear fusion. Okay, so this is the energy generation in stars. So as we saw in fusion, two lighter nuclei fuse together to form a larger nucleus. And when the fusion is happening, like when they are fusing together, energy is released. Okay, and we saw that the binding energy is going to, kind of reduce because they are, tightly bound. And some of the reactions that are, that happen is when your hydrogen, okay, two hydrogen atoms are kind of fusing together. Okay, so you have 2 plus 1. It gives out one positive beta, okay, plus your neutrino, okay, and plus energy. Okay, so this is your fusion. Then if you have, say, deuterium, okay, which has 2H, okay, so if you have deuterium that is, kind of fusing together, what you get is the helium isotope with 3 atomic mass number, okay, and then again you have a neutron that is produced, and you have energy coming out, okay, being emitted. Okay, then again another reaction that can happen with fusion is your again two deuterium nuclei coming together. It is forming tritium plus one hydrogen, okay, and it is giving out the energy. Okay, so you can see that the energy kind of increases, okay, as per the different reactions that you have. So obviously in the first reaction, two protons are combining, okay, to form a deuteron, okay, and positron, and it is releasing the amount of energy. Okay, so for fusion to take place, the two nuclei that are fusing together have to come much close. Okay, it has to come close enough so that the attractive short range nuclear force is able to affect them. Okay, since it's positive positive, two protons are trying to fuse, obviously it is going to start getting repulsed, okay, due to the coulomb repulsion that is there. But the energy that is needed to overcome this barrier must be higher, okay, and the height of the barrier, okay, this coulomb barrier that is there, it depends on the charges as well as the size or the radii of the two interacting nuclei. Okay, so you can see that it has to be like around 400 kilo electron volts, okay, and it is will be usually higher for nuclei with higher charges. Okay, and when this fusion is happening and the energy is supplied, the energy is, it can be equivalent to the temperature. Okay, the higher temperature is then required. Okay, so the temperature, okay, that we can, yeah. So you can, have the temperature, the estimate of the temperature that is required, where the two protons in a proton gas would have enough energy to overcome this Coulomb barrier. Okay, so that would be 3 by 2 K. P is equals to K. Okay, so that is 400 volts. Okay, where then your T comes out to be 3 into 10 raised to 9 Kelvin. Okay, so you can see that a very high temperature is required, and such high temperatures can only be found in stars. That is why, it's a kind of energy that is there in the generation of stars like sun, for example. Okay, so when fusion is achieved by raising the temperature of the system, okay, so that the particles have enough kinetic energy to get over the Coulomb repulsion, and so this is called a thermonuclear fusion. So thermonuclear fusion is the source of energy, that is there in the, interior of the stars where the energy is generated. Okay, so as you know, the interior of the sun has a temperature of, of the order 10 raised to 7 Kelvin. Okay, so which is actually less than the estimated temperature that we just found for the, fusion of particles of average. So clearly you need a kind of a, different kind of protons, which are, which have energies much above the average energy. So what happens is that, there is a multi-step process that is involved. Okay, so the multi-step process that, happens on sun is actually hydrogen, hydrogen, yes, hydrogen. Okay, you have two hydrogen giving you deuterium. Okay, and your positive, the positron, then V, and plus 0.42 MeV. Okay, then this again, the positron and the electron undergoes gamma. Okay, sorry, there's no positive here. So gamma, gamma decay along with your energy. Okay, now your this deuterium that is given out, okay, then it will attach itself, or it will fuse together with one hydrogen, then you get your helium isotope. Okay, and you have one more gamma coming out. Okay, so there's a gamma decay, and sorry, not gamma decay, or gamma radiation is given out. Then your helium, okay, this isotope of helium actually fuses together. Okay, where you get your helium atom or helium nuclei. Okay, and you have the one more hydrogen and another hydrogen, and you have this big amount of energy, okay, that will again drive this reaction. Okay, so for the fourth reaction to occur, the first three reactions will have to occur twice. Okay, and in which case the lighter helium nuclei will start uniting, okay, to form the ordinary helium nucleus. Okay, so the the net effect. Okay, so the net energy that is actually found is going to be 26.7 MeV, or mega electron volt. Okay, this is when the number of this three reactions has to happen twice. Okay, and then you get the four hydrogen atoms to combine, okay, to form this helium, okay, with a release of 26.7 mega electron volt. Okay, so this is the large amount of energy that is generated due to nuclear fusion, okay, that happens on the stars or the sun. Okay, so this is, the age of the sun is about, 5 billion years, and it is estimated that there is enough hydrogen in the sun to keep it going for another 5 billion years. Okay, So then when the fusion keeps happening, and there is the temperature is kind of the hydrogen is actually depleted and everything becomes helium, your star begins to collapse under its own gravity, and it will just increase the temperature, and then again the temperature, your helium will get kind of fissionized. Okay, it will get either fission or it will turn into a different kind of an element. Okay, so this is a kind of a cyclic process, and obviously once the hydrogen burning stops and the sun will start cooling and it will start to collapse, and then again it will raise the core temperature. Okay, and this then your temperature will increase, then a different kind of reaction will take place. Okay, so this is how nuclear fusion takes place. Okay, so that's it. This is the last part, and obviously you can also have thermonuclear fusion, which could be in a controlled manner also. There are very few examples where controlled thermonuclear fusion is used to generate the electricity. Okay, so thank you for attending, and hopefully this helps you.